Section 2, Quantum Theory and the Atom. Okay, we know we're still working on the parts of the atom. We know about the nucleus, that it has the neutrons and the protons, and it is the heaviest part of the atom. We are still working on the electrons. We're not exactly sure, scientists aren't still exactly sure what's going on with the electrons. So in the objectives for this section, compare the Bohr and quantum mechanics model of the atom, explain the impact of de Broglie's wave-particle duality and the Heisenberg uncertainty principle on the current view of the electrons in an atom. Identify the relationships among a hydrogen's atom's energy level, sublevels, and atomic orbitals. Now, don't let all these big words freak you out because you're going to work with this enough that it's going to be pretty self-explanatory. Review of vocabulary: atom, the smallest particle of an element that retains all the properties of that element, is composed of protons, neutrons, and electrons. Okay, new vocab for this section: ground state, quantum number, de Broglie equation, Heisenberg uncertainty principle, quantum mechanical model of the atom, atomic orbital, principal quantum number, principal energy level, and energy sublevel. Main idea: wave-like properties of electrons help relate atomic emission spectra. Remember, that's what we've been working with the last couple days. Energy states of the atom and atomic orbitals. All of those are related together. Okay, and through this we're going to figure out how. Okay, so Bohr came in and he predicted that the frequency lines in the emission spectrum of hydrogen, just hydrogen, was the only one he worked with, or the only one he got that he understood. So he predicted those, okay, and he stated the lowest allowable energy state of an atom is called the ground state. This is going to be the one closest to the nucleus. When an atom gains energy, it moves to an excited state. Bohr suggested that an electron moves around the nucleus in certain circular orbitals. Okay, as shown here, these darker circles would be the orbitals. And you can see ground state, the one closest to the nucleus. As it gets excited, it moves away from the nucleus. Okay, each orbital or each circle was given a number called the quantum number. Remember when we talked about quanta being the amount of energy that it can gain or lose? So the one closest to the nucleus was N1. As you move away, N2, N3, and so on. Okay, so when we talked about hydrogen, hydrogen only has one electron, so it has an N1, which is in its ground state. Then he stated that when energy was added, it moved to the N2. Let's look at, this is called the Balmer series, and it talks about, these are the visible, these are the ultraviolet, and these are the infrared. Remember, as you go through the electron emission spectrum, you have the different wavelengths. Now, I'm going to take you out of here, and we are going to look at this animation. Not sure if I can make this big enough, but you can get this on Glencode too. So we're going to watch what this is.
An electron, which is in a higher energy level than its ground state, is said to be in an excited state. When an electron moves from a higher state to a lower state, a photon is emitted whose energy is equal to the energy difference between the initial and final states. This principle is illustrated here for an atom through the mechanical analogy of a ball on a staircase.
Okay, so you can see
the transitions which produce photons of visible light for the hydrogen atom are referred to as the Balmer series.
So you can see as it goes down energy levels or down the stairs, it's emitting light. Now, these should look like the bands from the emission spectrum that you did on your labs. with mercury and neon and lithium. So as it goes down a series, as it's going back towards the ground state, is when it actually gives off that light. Okay, so now we're going to go to the next slide. And that's what Bohr was saying here. So now we're going to go look at, got to move this stuff out of the way. Okay, let's look at what this one has to say.
One of the observations confounding atomic scientists in the early 20th century was that an electrically excited element emits light that has a spectrum consisting of discrete lines rather than a continuum of wavelengths. For this to happen, the energy of the element's atoms must be able to change by discrete amounts. Let's see how spectral lines in the visible region of the electromagnetic spectrum arise for the simplest atom, hydrogen. In this thin vertical tube, hydrogen gas has been excited by an electric current. The molecules split into separate H atoms, which absorb electrical energy and then emit light. The spectroscope separates this light into individual wavelengths, which appear as lines in the spectrum. Look through the eyepiece to see the 4 major lines in the visible spectrum of atomic hydrogen. Now we'll explore how they arise. This small bright sphere represents the ground state hydrogen atom. In this most stable state, the atom is in the n=1 energy level, and its single electron occupies the 1s orbital. When the atom is excited, and depending on the amount of energy it absorbs, the electron can occupy one of several higher energy orbitals, such as the 2s orbital, the 2p, the 3s, the 3p, the 3d, and so forth. For example, here, a ground state H atom in the gas discharge tube absorbs enough electrical energy for the 1s electron to occupy the 2p orbital. And then, before it emits that energy as light, it absorbs even more energy, and the electron occupies the 4s orbital. Whenever the excited H atom drops to the n=2 level, it emits a photon with one of 4 specific wavelengths in the visible range. To see how the 4 spectral lines appear, we'll look at some of the possible transitions from higher energy s orbitals, whose boundaries are indicated by the dashed circles, to the 2p orbital in the center. Many other transitions can occur as well. Now, as the film strip unfolds, watch these photons emerge. The lowest energy transition is from the 3s to the n=2 level, and the emission is a photon of red light, which has the longest wavelength. More energy is emitted with the transition from the 4s to the 2p, and it appears as a photon of green light. A still higher energy transition occurs from the 5s to the 2p, and the emission is a photon of blue light. And the highest energy transition occurs from the 6s to the 2p, which appears as a photon of violet light, whose wavelength is the shortest. Lines in other regions of the hydrogen spectrum arise when the excited atom undergoes transitions to other final energy levels. Thus, the ultraviolet lines arise from transitions to the n=1 level, and infrared lines from transitions to the n=3 level. Only an atom whose energy is quantized, that is, exists in certain discrete amounts, can give rise to spectral lines.
Okay, so hopefully
One of the observations confounding atomic scientists in the early 20th...
Sorry about that. So that hopefully that helps explain this model. As the electrons are coming, they've already been excited from the ground state, and they've moved up into different energy levels. As they're coming back down is when they emit their light, not when they're going up, but as they're coming back down. I'm going to stop this video, and we're going to have a part 2 as well. because this one is a